One of the most important topics in any physical geography class is understanding why Earth has seasons. The late night comic Jay Leno always goes out to various college graduations like Cal State nurseries asking graduates why are there seasons, and undoubtedly he finds morons that never learned. Really, I believe that every high school graduate and actually every person living in our planet needs to understand why seasons occur. And it's a shame that this information often waits until a GPH 111 class in college. This outline gives you the general order of information that I will present. However, before I get into seasons, I'd like to kick back and discuss the structure of physical geography and that we are really moving into a subset of physical geography dealing with climate and weather. In general, to understand the nature of place, the physical geography of place, it often starts with the climate of the area. It's the combination of climate, plants and animals, soil, geology, the landforms, and the hydrology that allow you to characterize the physical geography of a location. And seasons is really the start of understanding climate. What somebody means by seasons varies depending upon where you are in planet Earth. If you are in the northeast, you'll have 4 seasons. If you are in the Sahel, between Sahara Desert and wet tropical Africa, there are 2 seasons. A dry season that takes place really from October all the way through June, and then a wet season that occurs just in the months of July, August, and September. So let's start with the basics of Earth systems before we try getting into complexity of why seasons are different from place to place. Earth revolves around the sun about every 365 and quarter days, and then Earth itself rotates once every 24 hours. The rotation is counterclockwise if you are looking down at the North Pole. So you have the Earth going around the sun, and the Earth is tilted 23.5 degrees with respect to the plane that the Earth and all the other 8 planets move on. This is called the plane of ecliptic. And so the Earth moves in counterclockwise direction looking down at the North Pole, or while it spins in a counterclockwise direction looking down at the North Pole. And all this while the axis of the Earth is tilted 23.5 degrees, where if you're up at the top of Earth on the North Pole and you look straight up at night, you will see Polaris or the North Star. The Earth's orbit around the sun is slightly elliptical. This means that there are some times in Earth's orbit where we are closer to the sun and then farther away. We are close to the sun at perihelion on January 3rd. We're 3 million miles closer to the sun than we are on July 1st. So if you're thinking that Earth's seasons are produced by when we're close to the sun, it being summer, and when we're more farthest away from the sun, being winter, that's obviously incorrect. If you live in the northern hemisphere, you know that to be blatantly false. Something else has to be cause of seasons, and it's definitely not how close we are to the sun. This simple explanation for seasons is that we have a tilt to planet Earth of 23.5 degrees. But exactly why the tilt produces seasons is a bit more complicated. Let's start off by recognizing that we have a northern hemisphere and a southern hemisphere split by the equator, and that the seasons are opposite in each hemisphere. There are 2 different reasons why axial tilt produce seasons: the length of daylight and the angle of the sun. It would be, I hope, somewhat obvious that if there is a longer day, you are receiving more solar radiation and therefore it will be warmer. Similarly, I hope it would be obvious that if the sun is more directly overhead, the sun's rays are stronger and hence it would be warmer. So this diagram illustrates how sun angle and length of day would change from mid-latitude perspective. The sun rises in the east and sets in the west, and the length of time that the sun is visible in the mid-latitude, such as over the United States or South Korea, is proportional to the length of the arc that you see. So during the winter solstice, you will notice that the blue arc is very short, and that represents a relatively short period of time that the sun is in the sky. During the equinoxes, the yellow arc shows that the sun is in the sky a little bit longer, actually 12 hours. And in summer solstice, there is a much longer period of time when the sun is actually in the sky. Similarly, this diagram illustrates that the sun angle will change that when the sun, let's take a look at its noon position in summer solstice, is almost directly overhead. That's the Z position. In the equinox, as the sun has a lower angle, and in the winter solstice, the sun is in a much lower angle. The reason why sun angle is so important is that the sun's energy package can be spread out if the angle is lower, as illustrated in this diagram. This diagram shows an equinox condition when the sun is directly overhead at noon at the equator. And so towards the North Pole, the sun's rays on March 21st and September 21st are spread out as opposed to at the equator. When all the sun's rays are directly overhead and the full brunt of the energy is aimed directly at the equator. At this point, it might be helpful to review the key latitudes that relate to the seasons. There's the equator, the two tropics, the Tropic of Cancer and the Tropic of Capricorn. A good way to prevent them from being confused is it's always a can of corn. Cancer, Capricorn. It's never a corn of can. So from the top to the bottom, it's Cancer and Capricorn. Can of corn. On June 21st, the Northern Hemisphere summer solstice, the sun's rays are directly overhead at noon on the Tropic of Cancer. On the equinox, the sun's rays are directly overhead at noon on the equator. And in the Northern Hemisphere's winter solstice, December 21st, the sun's rays are directly overhead at noon on the Tropic of Capricorn. The sun's rays are never directly overhead at noon ever to the poles of the Tropic of Cancer or the Tropic of Capricorn. So between the Tropic of Cancer and the North Pole, the sun is always to the south. The sun is never directly overhead at noon. The Arctic Circle and the Antarctic Circle become important because they're where you'd have 24 hours of daylight from the Arctic Circle to the North Pole during summertime on the summer solstice. And on the winter solstice, from the Arctic Circle to the North Pole, you'd have 24 hours of nighttime. And the reverse is the case for the Antarctic Circle during our summer. From the Antarctic Circle to the South Pole on June 21st, there is 24 hours of nighttime. And on December 21st, our winter solstice, the Antarctic Circle to the South Pole experiences 24 hours of daylight. So let's review all this from the perspective of the equinox. This is when the sun's rays are directly overhead at noon at the equator, when all latitudes experienced 12 hours of night and day. And another way to look at it is in the upper right-hand diagram, where the Earth's tilt is not making either hemisphere lean towards or away from the sun. Even though the Earth's tilt is still 23.5 degrees, there's no preferential leaning in the orbit on March 21st and September 21st. So another way to view the equinox would be this diagram, where those yellow rays represent the sun striking the Earth. All latitudes have an even amount of night and day, and you will note that the sun angle gets lower and lower when you move from the equator towards the poles. This video shows that Earth's northern and southern hemisphere are receiving the sun's rays about equally around equinox time. So let's think about the length of the day just for a little bit. It's always 12 hours of night and day at the equator. But as you move away from the equator and as you move towards the solstice, the length of day gets more extreme. So let's think about it from the perspective of the diagram on the left in the northern hemisphere summer. During the solstice condition on the equator, it's 12 hours of night and days, and as you move towards the North Pole, the length of daylight gets longer and longer until you reach the Arctic Circle, where it's 12 hours of daylight year-round. Now let's still look at the diagram on the left-hand side, and as you move away from the equator towards the South Pole, the length of daylight decreases. That would be colored sky blue until you reach the Antarctic Circle, where there's 24 hours of nighttime. The opposite is true in other solstices. So when it's the December solstice, which is the diagram on the right, the Antarctic Circle now has 24 hours of daylight, and the Arctic Circle has 24 hours of nighttime. Here's yet another diagram that illustrates the solstice position on June 21st. Take a look at the upper diagram. Here, the northern hemisphere is leaning towards the sun, so everybody up at the Arctic Circle, as the Earth spins counterclockwise, looking down at the North Pole, is bathed in sunlight. It's a low angle sunlight, but it's 24 hours of sunlight. It's a reason why it's summer in the northern hemisphere. Also, note that on June 21st, the sun's rays are vertical at the Tropic of Cancer. So everybody in the northern hemisphere has higher sun angle, which means the sun's rays are more intense. And everybody in the southern hemisphere has a lower sun angle and shorter length of day. This is for the June 21st solstice position. And yet, this is another diagram to illustrate the asymmetry in daylight on the summer solstice and how the sun angle changes, where you're about 23.5 degrees, which is your angle at the North Pole on summer solstice when it's noon. It's summer solstice, so northern hemisphere is receiving more sun's rays than southern hemisphere. I'm hoping that your increased perception of the importance of sun angle may alter how you deal with your living environment. For example, in metropolitan Phoenix, shade in the summer is a vital concern. So, if you had a mountain to shade you, what side would you live on? In other words, if you live in a desert climate like Phoenix or Tucson, and if you had your choice, would you rather be on the south side of the mountain or the north side of the mountain? I don't know about you, but I'd rather be on the north side where I'm shaded because the sun is rays to the south. Now, let's review the December solstice, which is December 21st. In this situation, from the Arctic Circle to the North Pole is 24 hours of nighttime, and all the conterminous United States has a shorter length of day. But in the southern hemisphere, the sun's rays are directly overhead at noon on the Tropic of Capricorn, and all the latitudes have longer daylights. So it's summer, because the sun rays are more intense and you get more time during the day to receive the sunlight. This is shown with a little bit different perspective in the upper diagram, where you can see changes in the length of day. As the sun moves throughout the sky, in this particular location would be New York City. So during the June solstice, you have the sun higher in the sky and you see it for a longer period of time. And on the December solstice, you see the sun just for a few hours in New York City, about 8 hours I think, and in a much lower angle. And this is yet another diagram illustrates that when northern hemisphere is tilted away from the sun on December 21st, you have much lower angles and shorter day lengths. It's winter solstice, so northern hemisphere is receiving less sun's rays than southern hemisphere. Here are 3 different fun visuals about winter solstice. In the upper left-hand diagram is Stonehenge on winter solstice, where the sun is in a particular distinctive position, and then you have sun tracks made in New Mexico, where you can see just how low the sun gets on the northern hemisphere winter solstice. And the right-hand side is a photograph that shows in the Arctic Circle it's not completely dark, in that at noon you have a persistent twilight even if the sun never quite makes it above the horizon. This is yet another diagram that may work for you to see that on the solstices from the Arctic Circle to the poles and from the Antarctic Circle to the pole, you either have 24 hours of night or 24 hours of daylight depending upon which solstice and where you are. Let's first take a look at the Northern Hemisphere summer solstice and the photograph in the upper right hand corner. The photograph shows a series of clicks of the camera at different time intervals towards midnight just above the Arctic Circle. So what's happening here is the sun is never setting. It's always staying above the horizon, illustrating that there's 24 hours of daylight north of the Arctic Circle on the summer solstice. Then take a look at the photograph on the far lower right that says what latitude. This is a photograph of babies in Siberia that are getting their exposure to the sun because up in the Siberia, you are at a latitude that receives very little sunlight during the winter time, and so they need their vitamin D. Now, take a look at the middle image on the right hand side that asks question on December 21st at noon, right? So this is at noon. The sun is barely peeking out above the horizon. So it's just rising at noon on December 21st. Where would this latitude be? Think about it for a few seconds and then I will explain the answer. Okay, here's the way to think about it. On the Arctic Circle on December 21st, which is the winter solstice, there's 24 hours of nighttime. As you creep towards the equator, you get a little bit more daylight. For every latitude, the daylight gets a little bit longer. So this photograph would be taken just south of the Arctic Circle, say in Alaska, southern Alaska on December 21st. You can see the sun just for a little bit when you're south of the Arctic Circle. Well, after the Challenger's tragedy, this image was sent out over the internet in, I'm sad to say, educational circles and listservs by individuals who simply didn't understand physical geography or the seasons. The claim over the internet was that this image was one of the last ones taken by Challenger from outer space before the tragedy. So, knowing what you know now, why would such a claim be utterly insane? Well, first of all, you're probably looking at the ocean floor topography and you're seeing the mid-Atlantic ridge, and you'd know that no snapshot, no photograph, no image from outer space would reveal the ocean topography, right? Secondly, you'd be thinking, where are the clouds? And third, as pertain to the seasons, you'd be looking at the line or the terminator between night and day that on January 28th. That's very close to the winter solstice. You would know that up in Scandinavia, you would never have a terminator line that would look like this. There would be much more night. So everything about this image, from the lack of clouds to the topography of the oceans, would indicate that this was fake. In summary, if you're looking for a single diagram that encapsulates the entire discussion, this one from NOAA and NASA really boils it down to the nuts and bolts that the tilt of the Earth is the reason for seasons. Because the tilt of the Earth makes sure that during the summertime, the latitudes tilted towards the sun have longer days to receive more sunlight, and the sun's rays are more directly overhead, so they are more powerful. We'll continue the discussion in class, going through the study guide questions and dealing with issues you might have to help visualize this material. It's rare that a person gets it right at the first glimpse, which is the reason why I've shown different diagrams and different formats. And it's important that you come to class and ask questions that you have on how you perceive the reasons for seasons.